Welcome to another video tutorial. This time we're looking at binary fractions. So far we've only looked at whole numbers, in programming terms referred to as integers. We now need to understand how computers represent fractions. Now in primary school you would have looked at decimal fractions and how they work. Let's put one down. We've got 12.75. We know through our schooling that we've got 12 whole numbers and 0.75, so 3/4 of a whole number. And we know that because we know that we have our units column here, our tenths, and if we had any more, our hundredths, and past the decimal point we know that we have got a tenths column, a hundredths column. Now in the same way binary fractions work. So let's have a look at 12.75 in an 8-bit binary with 4 bits after the binary point. So let's have a look. Let's give ourselves our headings as we would normally. So we've got 1, 2, 4, 8. This column I'm going to leave free because I'm going to put my decimal or binary point in it. Past this we have half. So this side of the binary point we're timesing it. So it's doubling it every single time. Okay. This side of the binary point we are halving it. So half of one is half. Half of a half is a quarter. Half of a quarter is an eighth. You can see that. And half of an eighth is 1/16. Now this, you're going to need to know the decimal equivalents of these, which I'll come to in a minute. But those are our headings for now. And now let's put our number in. So we've got 12.75. And I'll put the number in and I'm going to show you how you work it out. Now why does this work out? We can work out this because you guys already know this half here. We've got one lot of 8, one lot of 4, which gives us 12. Okay, so we know that's the 12 part of it. But what about this side here? We need to know the decimal equivalents of these fractions. That's really important, and you're just going to have to learn them. I'm hoping that you know the decimal equivalent of a half is 0.5. The decimal equivalent of a quarter is 0.25. The ones you're going to need to remember is that an eighth is half of 0.25 because you're just halving it. So it's 0.125. And half of that again, 1/16, is 0.0625. You can see that there, a little bit out of focus. And in exactly the same way we add these up. So we've got 0.5 here, we've got one lot of 0.5 and we've got one lot of 0.25, so we add those two together. So I bring my hundredths down, I bring my tenths down, and I have 7/5. Now you should notice that for the same number of bits after the point, the binary fraction provides less accuracy because it can only take 4 different values, whereas a decimal number can have 100 different values with 2 digits. Now you'll see in a moment how this actually causes a little bit of trouble. before that, let's do a worked example. We're going to convert the number 6.125 into a binary fraction. So let's have a look. We've got 6.125 and we want to convert that into a binary fraction. So let's do our grid again. We've got 1, 2, 4 and 8. Put a decimal point down here. Now we've got a half, a quarter, 1/8, 1/16. Okay, and we know that that equates to 0.5, 0.25, 0.125, 0.0625. Now the 6, that's easy enough. We've got one lot of 4, one lot of 2. But what about the 0.125? Well, that's quite simple, because we're going to 0.25 is too large. 0.5 is too large. 0.25 is too large. 0.125. One lot of those. No lots of those. So that's a really nice easy one, because 6.125 fits in perfectly with our system, our number system. But a more interesting number is 6.4, and this here is where the accuracy becomes a problem. So let's move over here a minute and redraw our grid. 1, 2, 4, 8. Half, quarter, 1/8, 16th. Okay. Now 6 again. No lots of 8, one lot of 4, one lot of 2, no lots of 1. And we've got a 0.4. Now we can't have any lots of 0.5 because 0.5 is too big. So 0 lots of that. Now we can have one lot of 0.25. So that gives us 6.25. We can also have one lot of 0.125, because that gives us 0.375, adding those two together. But if we added another 0.0625, that would take us over 0.5, 0.4. That would take us bigger than that. If we added another 0.0625, adding those together would give us 13. Would give us 0.4375, and that is too big a number. We can't ever go over what we have got here. So unfortunately, 0.375 is the closest we can get, and that's okay. A computer might restrict you to the number of bits you can use, so we have to just use a number closest to the one we're aiming for. Now you could feel a bit annoyed by this, but whenever you're doing a third, calculating a third in decimal, that never fits either. You've got 1.3333 recurring, because it never quite fits. You can't ever get a third, an exact third, because 10 doesn't divide by 3 exactly, and we just accept that in decimal, so we have to accept this in binary. Now what we could do for greater accuracy is to add on another bit to the right of the binary point. So for greater accuracy, we'd add on more bits to the right of the binary point, and for a larger number we would add them on to the left. That's something that you may also be asked in an exam with a question or for a binary fraction. These are also referred to as unsigned floating point numbers. So if that came up in the exam, it means that it just has a binary point. But it will also tell you how many bits to the left and how many bits to the right. So if a question pops up where accuracy is a key factor or a mark is assigned, asking you a question about accuracy, you would indicate that for greater accuracy you would need to add a bit to the right, but this would be the correct answer. Now that's as complicated as it gets. You do need to practice these, you do need to remember the decimal equivalents, and it's just a process of adding them up. And once you've done that, you practice the examples on the learning platform and you'll be just fine. Until next time.